Students, I am going to discuss about one type of datum system in this session. So this is called group datum plane, spigot and tongue assembling with a group of datum plane, recess and gap. If you look at these two diagrams, on one component we have got a datum plane, spigot, this is the spigot, and a tongue. So in one member you have got a datum plane, spigot and tongue. In another member we have datum plane, this whole is called recess and gap. So in another member you have got a datum plane, recess and gap. So when this part is assembled onto this part, all the 6 degrees of freedom of this part is arrested with respect to this part. So this datum system is used to arrest all the 6 degrees of freedom of one member with respect to the other member. When this datum plane is assembling onto this datum plane, 3 DYF is arrested, and when this spigot is assembled onto this recess, 2 more degrees of freedom are arrested. When this tongue is assembling in the gap, 1 more degrees of freedom, that is the rotation about the axis Z, is getting arrested. So all the 6 degrees of freedom of one member are arrested with respect to the other member. When you choose a fit between the spigot and recess, a location fit is preferred. In this example, the same component, 2 components are drawn using orthographic views. This member is the top member whose isometric view is shown here, and this is the orthographic view of this member. So in this example, the spigot is assigned with a tolerance of 110 H8, and the recess, so this is the hole into which the spigot will get assembled. This recess is assigned with a tolerance of 110 H8. So a location fit of H8 is assigned between the spigot and the recess. When you assign a location fit, there can be a small clearance between the recess and spigot. So this small clearance may introduce some locational error with respect to the translation in X and Z direction. So this spigot, when it is assembled onto the recess, due to the small clearance existing between the spigot and recess, the location, the translation degrees of freedom about X and Y of this member is not fully constrained. So that calls for locational inaccuracy in translation. We have to determine what is the inaccuracy due to the clearance, small clearance existing between spigot and recess due to the location fit. Similarly, when you insert this component over to this component, there is a clearance between the width of the tongue and width of the gap. So due to this clearance, the rotational degree of freedom of this member about the z-axis is not fully constrained. So still you can able to rotate this component after inserting into the bottom component little bit, not fully, a little bit can be rotated. So that calls for locational inaccuracy in rotation. We have to determine these 2 locational inaccuracies using the values given in this example. First, we will discuss about how to find the locational accuracy of this member in translation. So the fit between the spigot and recess is 110 H8, 110 H8, 110 H8. So using these 2 values, we have to determine the locational accuracy in translation. So the 110 H8 has a tolerance of plus 0.0 plus 0.54. The 110 H8 has a tolerance of minus 0.0 minus 0.54. So when you assemble these spigot and recess, the maximum clearance occurs when you assemble the biggest hole with the smallest shaft. So the biggest size of the recess is 110.054 as per this tolerance. Smallest size of the spigot is 0.946 as per this tolerance. So the maximum clearance is 0.108. The minimum clearance is 110 minus 110, it is 0. The mean clearance is, taking the sum of these two divided by 2, you get 108 plus 0 divided by 2 is equal to 0.054. From the 0.054, the upper maximum clearance is varying by plus 0.54. From the mean clearance of 0.54, the minimum clearance is varying by minus 0.54. So from the mean clearance of 0.54, the maximum and minimum clearances are varying by plus or minus 0.54. So the location accuracy in translation for this example is arrived as 0.054 plus or minus 0.54. So this 0.054 plus or minus 0.54. So this is the location accuracy in translation for this example. Next, we have to find the location accuracy in rotation. So before we find the location accuracy in rotation, we have to determine maximum size of the width of the tank. So this W we have to find based upon the assigned values of tolerances. This W is the width of the tongue. This tongue is going to be assembled in the gap. This gap is assigned with a tolerance of 12 H tongue. And if you look at this, a gap has to be machined on the component. This slot has to be maintained, has to be machined exactly radial to the axis of the recess. So it is not possible to locate the slot at exactly radial to the axis of the recess. To allow for some error, we assign a position tolerance of 0.05 applicable at MMC, taking the C and D as the data. C is the top surface and D is the axis of the recess. So taking C and D as the datum, a position tolerance of 0.05 is assigned to the gap to control the symmetry of this gap with respect to the axis of the recess. Similarly, on the top component, this tongue has to be placed exactly radial to the axis of the spigot. Since it is not possible to exactly perfectly locate the tongue at a radial position, we have to control the symmetry of this tongue by assigning a tolerance. A position tolerance of 0.2 is assigned to control the symmetry of this tongue with respect to the spigot. So taking the A as the datum, and A is the this datum's plane, and B is the axis of the spigot. So taking A and B, the position, the symmetry of this tongue is controlled within a tolerance of 0.2 at MMC. Now let us apply these values to find the maximum width of the tongue W. So the maximum width of the tongue W is found using this formula: MMC size of the gap minus position tolerance of the gap plus position tolerance of tongue plus working clearance. So first we have to find the MMC size of the gap. Now the gap is assigned with a tolerance of 12 H tongue. So the 12 H tongue, if you look at the tolerance for 12 H tongue from the data book, you will find the MMC size is 12 for the gap, minus the position tolerance of the gap is 0.5 as given here. So 0.5 is the position tolerance assigned to the gap, 0.2 is the position tolerance assigned to the tongue. So if you consider these two values, 0.5 plus 0.2 plus working clearance is taken as 0 for this example, and when you consider all these values, the maximum size of the tongue W is arrived as 11.75. From this I can find the maximum angular plane. So what is the meaning of maximum angular plane? When you assemble this onto this component can be little bit rotated about this axis Z. What is the maximum angle by which this component can be rotated onto this one? So that is called maximum angular plane. So the maximum angular plane is arrived considering the various clearances between the spygard, recess, tongue and cap. So tan theta is equal to maximum play between spygard and recess plus maximum play between tongue and cap divided by the distance between tongue and spygard. So the maximum play between spygard and recess is arrived. So the maximum size of the recess is 110.054. The minimum size of the spygard is 109.046. Referring to these tolerances, we have found out the maximum minimum size of the tongue and cap. So maximum minimum size of the spygard and recess. So 110.054 minus 109.946 is the maximum clearance prevailing between the spygard and recess. Similarly, maximum play between the tongue and gap. So we have to find the maximum size of the gap, we have to find the minimum size of the tongue. So the maximum size of the gap is found by referring to the 12H10 tolerance. So the 12H10 tolerance is plus 00 plus 0.7. So the maximum size of the gap is 12.07. This would be minus. So minus what is the minimum size of the tongue? So the tongue is found as 11.75. W is found as 11.75. This tongue width is given assigned with the tolerance of minus 00 minus 0.5. So 11.75 minus 00 minus 0.5. So what is the minimum size of the W? So 11.75 minus 0.5. So 11.7. So 11.7 is the minimum size of the tongue. So when you consider these values, you can find the value of the numerator. The denominator is the distance between the tongue and spygard. So what is the distance between the tongue and spygard? This tongue is extending from the spygard to the outer diameter of the component. We have to find the middle plane of this. This is extending from this point to this point. Find the middle of this one. From this middle, find the distance between the this middle plane and the axis of the spygard. So that is the distance between the tongue, middle plane and the spygard. So this can be found out using the dimensions 210 and 110. So 210 plus 110 is 320. 320 divided by 2 is 160. So 160, if you draw a circle at 160, it will be passing along the middle plane of the tongue. So this circle of diameter 160 will pass through the middle plane of the tongue. So since this is having a diameter of 160, half of that one is 80. So 80 is the distance between the center of the spygard and middle plane of the tongue. So 80 I have substituted in the denominator. So if you work out the value, tan theta comes to 0.00595. So from this, the theta value is taken as tan inverse of 0.05975, which is equal to 0.342 degree. So the 0.342 degree is the maximum angular plane for this example. So what the meaning is, when you assemble the top component to the bottom component, the top component can be rotated by an angle of 0.342 degree. So the mean angular plane is taken as half of the maximum angular plane. Half of 0.342 is equal to 0.1712. So the location accuracy in rotation for this example is 0.1712 degree. If you convert this into minute, you have to multiply with 60, and you are getting 10.27 minutes of a degree is the location accuracy in rotation for this example.